Yes, hello together. New week and back in statistics. We are in the field of estimation, confidence intervals, and hypothesis testing. We've started the last week, but we had left one exercise from last week, and this we will do as a starting point today. So let's take this exercise number 4, copy and go into the presentation. Here we are. And I need my screen. A bit larger. So since in the other exercises we had already confidence intervals for the mean, confidence intervals for the mean given a normal distribution, or in the case of small sample size using the t-distribution. But of course, sometimes we also asked to give a confidence interval for the variance or the root of the variance, the standard deviation, and this we will do in exercise 4, sheet number 2. So a provider of mobile games collected the playing time of 120 randomly drawn users. Well, this is something you are faced with, I think, every day in internet. If you want to have some information, if you creating an account, then you are always asked, well, I will take your data and I will use this data analyzing my users and so on, and nothing else we have here. So we have a mobile game on your handy, on your tablet, and then the providers of these games want to know how long do you play on average, and so they take just a random sample of n equals 120 users, and yeah, then we take just the data of these x1, x2, x120 guys, and summing up all the specific data of our 120 guys, we obtain the sum of all guys will be 21,840, and the sum of time played squared is 1868856. So we are just, oh, this is a bit here, so to move this is okay. Let's see. Almost. This one. Okay, this works. So in this case, we do not have the single data of xi, x1, x2, x3, and so on, but we have the aggregated data. And now we are asked to calculate a confidence interval for the variance for the playing time of a confidence level of 99%. So first of all, from our data, we need an estimator, an unbiased estimator. This I should have written here in the exercise, that we want to take the unbiased estimator for the variance, and the unbiased estimator we have shown for the variance is 1 over n minus 1 times sum over squared deviation from the mean. I from 1 to 120. So, thus, since we do not have the single values of xi, we cannot directly put in the data, summing up the deviation, squaring, dividing by n minus 1. We have only the aggregated data. And how do we come from these two aggregated numbers to these unbiased estimators? Just a question. I think you have seen this in your introductory courses, but also we have more or less done this also when we calculated the mean quadratic error. There, if we multiply these two brackets here, we obtain 1 over n minus 1 sum I 1 up to 120 xi squared minus 2 xi x bar squared minus x bar squared. And then remember our trick that we put in these brackets yet now a 0, adding plus mu and minus mu, and using this we obtain 1 over 1 minus n equals sum xi squared within the sum up to n minus 1 over n sum xi, and now the brackets outside my summation sign. Squared. Okay, and then I'm done. Since I have the sum of xi, this I can put in here, and I have the sum of xi squared. This I can put in here. And if I put these numbers in this formula, then I got 7512 more or less. Then sigma hat is more or less 7512 squared. And let's also write down the standard deviation. This is then given by 86.67. 86.67. This, of course, you can also just do with your calculator. But now comes the interesting part of this exercise. Calculate a confidence interval for the variance of the playing time given confidence level of 99%. And now this is different, or a bit different, to the case calculating confidence intervals for the mean, since for the mean we always have a symmetric distribution, t-distribution, and normal distribution are both symmetric distributions with respect to the mean, or in the standard case with respect to 0, and the chi-squared distribution, which we need for the confidence interval of the variance, is not symmetrically. So what we just want to calculate is the following area in the following diagram. Chi-squared distribution looks more or less like this. And what we want to calculate is, and now our number here, 7512, is maybe here. Then this number is not in the middle, but we want to calculate these two limits here, lower limit and upper limit, and again this area here should be, what do we have, 99%. And for this, oops, we just go back into our, no, this not, where do I have it? Lecture, not last week, but the week before, P8, so I need, there it is, P8, no, then it was P7, sorry. Here. That we know that yn minus 1 s over sigma hat is chi-squared distributed. Let's write this down. N minus 1 s squared over sigma hat squared is chi-squared distributed. And this just means, using this formula, we have to calculate, oh sorry, this is not correct. Over sigma squared, and here we have the sigma hat squared that we just calculate. N minus 1, this s squared is meant sigma hat squared, that we have to look up within a table or using some software program, statistic software, that we look up the lower value of the chi-squared distribution, 1 minus alpha divided by 2, so 99.5, and 0.5 with n minus 1 degrees of freedom. So we just have to calculate n minus 1 sigma hat squared over chi squared 1 minus alpha n minus 1. So the lower limit equals n minus 1 sigma hat squared over chi squared, in our case 99.5%, and n minus 1 is 119, and e upper limit is n minus 1 sigma hat squared over 0.5%, 119 degrees of freedom. So, using these numbers, this I have done for you in Excel. We have 1 minus alpha. Here, chi squared. Oh, you don't see this. Bit move to the right. So, these chi squared 1 minus alpha and 119 equals 162.5 approximately and 83. So let's also write this down. So sigma hat chi squared, chi squared, and here also chi squared of 99.5, 190, 162, what was it, 0.5, and chi squared 0.5%, 190, approximately 62, I think. No, 83, sorry. Roughly 83. And these two numbers from table or statistic software. This is, yeah, the same that you know that for a confidence level of 95% normally distributed, you use this number 1.96. This is the equivalent number just from the chi-squared distribution. Well, and putting these numbers in, here we have 7,512 times 119, and then we obtain, putting in these numbers, roughly 5,502 and 10,768. 5,502 and roughly 10,768. 10,768. So again, this formula here and this for the upper and lower limit, this looks quite complicated because we have here these Greek letters chi squared, and we have two indices, the alpha level number of degrees of freedom. But I think if you use this formula then it is always just putting in the numbers. But, and this, I want that you learn this from this lecture here, that you know what you are doing, putting the numbers into this formula. Because, again, quite often You have some data, you put it in your statistic software, pressing enter, some numbers come out, and then you say, well, here I have a really great result, but you are not able to explain what you have done, what your numbers which came out of your data really mean. And so we have another part B. Calculate the confidence interval of the standard deviation for a probability error of alpha is 1%. And this, I ask you, this is a really hard question. You see, I'm smiling because why is this a really hard question? If you have a look at what I've written here. Yes, just take the roots of the limits, of course. And that it is just taking the roots of the limits is that you just know that the standard deviation is the root of the variance, and you look here into the question and you have an alpha level of 1%, and this of course translates in a confidence level of 99%. So it is just the same question as A. You should give the answer for the standard deviation, and so just take the limits, take the root of the limits, and then we obtain lower limit and upper limit approximately. Do we have, where we are, here, 74.2 and 103.8. 74.2 and 103.8. And here again, if you put in between these two limits, the 86.67, which we have calculated as an estimator for our standard deviation, then we see that this number is quite close, but it is not in the middle of the interval due to the fact that the chi-squared distribution is not symmetrically. So keep in mind, chi-squared is not symmetrically. Okay, so we have done our last exercise, and then we step back to our lecture. And where is P8? This was this, then it should be here. Hypothesis testing. We started with hypothesis testing because now this is, yeah, of course, connected with calculation our confidence interval. But now we just have some hypothesis that maybe the awareness, we had this example last time, of my product within the demand structure has increased because I have done some marketing action, and I take a random sample. I just ask people, and I got out here in our example the question that 420 out of 1,000 people have answered they know my product. I knew that my product has been known by 40% of the people. So is it okay if I say that the awareness has increased because now I have 42%? But of course, this is a statistic experiment, and therefore I never can say I'm totally sure that since 420 over 1000 is greater than 40%, that the awareness of my product has increased. I only can say that for a given probability, or the other way around, for a given error. And here, quite often, we take 1%, 5%, or 10% error probability. Given this error, I can say, okay, assuming some distribution in behind, mostly we take, of course, the normal distribution, my awareness of my product has increased. I only can answer, yes, I know that the awareness have increased if I would ask the total parent distribution. So if I say here in Wilhelmshaven, I go downtown asking 1,000 people, then I can only say, given some error probability, that in Wilhelmshaven, 80,000 inhabitants, the awareness has increased. This we have done last week, and today we, of course, want to do also some specific examples. And for this, we have talked about this conceptually, and now I want to do what I have to calculate to answer this question. Given error probability 5%, do I have to reject my null hypothesis? Null hypothesis is the starting point. Mostly I say just my null hypothesis is the awareness does not has increased, nothing has changed. Although I have 420 people, can I reject these hypotheses, or do I still say up to a confidence level of 95%? I say, well, there are 420 people. This is larger than 400, but if I ask the next day another 1,000 people, it could be that there 389 people say, I know your product. So there is, of course, always, if I take a random sample, some statistic fluctuation. And this then means I'm calculating a test statistic, and this test statistic, we will see in a minute, is of course calculated via our estimators using the null hypothesis. So the mean 400 out of 10, 1,000 people, 40% does not have changed. This is then the assumption that I think still the mean is 40%, taking also our estimator calculated from our random sample, 42%. Taking these two numbers together, I obtain the test statistic, and this test statistic then I have to compare with a given critical value, and this critical value is obtained from the assumption of alpha. So this always changes if I say up to a level of 99%, up to a level of 95%, 90%, 99.9%, or so on. Then I always have to compare with different critical values. And this, again, I can do left-sided, two-sided, or left-sided, right-sided, or two-sided. And this always then means, and I have taken this here in the diagram, if I take a left-sided question, then the area below the left side should be up to my alpha level 1%, 5%, right-sided it is to the area below my distribution from the right side. And this, remember just our calculation in the last exercise, a two-sided confidence interval, of course, then corresponds to a two-sided test. And then I say, given a probability of 99%, can I reject that my mean of the distribution is still in between some interval? Means then just that these two areas together have to be 1%, 5%, or 10%. This is, yeah, more or less the same, or it comes from the calculation of our confidence intervals. So this was the theory, and then I think the best thing to do is just calculating some specific examples, of course, after I have shown you how to calculate the test statistic. And again, we just take these hypothesis testing, of course, for the normal distribution and the mean. And with this, we will start. And we want to take the maybe easiest case. So we say that we have a large sample. And if we have a large sample, then we can assume that everything is normally distributed. And then remember from our standardization, we have shown, or we have learned from the central limit theorem, that x bar minus the known mean over estimated standard deviation times square root of n is normally distributed, or if we have a small sample size, then we know that this variable is t-distributed. And now within hypothesis testing, we take it, yeah, more or less only the other way around, calculating the confidence intervals. We didn't have a number for the mean. So then we took this z value as given, dividing by square root of n, plus minus x bar, multiplied by the standard deviation. We obtained the lower limit and the upper limit of our confidence intervals. And now we just assume some value for this mean. And this is our hypothesis. This is our null hypothesis. In our example, then we assume nothing has changed. So the awareness of my product is still 40%. And in this case, we would have mu is 0.4 and X bar is 0.42. Our estimation, 420 people out of 1000 have said that they know my product after the marketing activity. Okay, but now we can go in the first example. Some machine produces boards with a minimum width of 10 millimeter. Board with less than the minimum width cannot be used. The machine has an accuracy of 0.75 millimeters. So of course, in practice, not every board can be cutted accurately with a 100% accuracy, but we have a fluctuation of 0.75 millimeters. We want 10 millimeters, and then we have a sample of 100 boards, and we just measure the length of our 100 boards. And then we see that the average width length of our boards is not 10 millimeters. This could, in practice, of course, only be in case of, could only accidentally be the case that we just have 10 millimeters on average. In practice, always if we take a sample of 100 boards, we will just obtain some number in the neighborhood of 10 millimeters, and in our case it should be 9.85 millimeters. And now we want to know, is there something wrong with my machine? Because on average, the length of my boards is not large enough. And therefore, we just say, okay, we take a confidence, we take an alpha error of 10%, a confidence level or significance level of 90%. And up to this error probability, is this just a random fluctuation, and I do not have to call anybody to have a look into my machine if there is something wrong. So then at first we start, what is then my null hypothesis? Is this shortfall significant? This means, hopefully, nothing is wrong with my machine. So the null hypothesis is, of course, just larger or equal 10 millimeters. So nothing is wrong with my machine. Everything is okay. The status quo. Great. So mu larger than mu null. So is larger than 10 millimeters. Then let's write the alternative hypothesis is then just mu is smaller than 10 millimeters. And then second, calculating the test statistics. there we have to look in the framework of our experiment, so to speak. N is 100. Since n is 100, we don't care about the distribution. We just say from the central limit theorem, more or less, we can assume that we have a normal distribution, and then we here in this case, A, n is larger than 30. This is more or less the rule of thumb that then we can assume the normal distribution. And so we calculate z is x bar minus mu over sigma hat times square root of n. So then that equals x bar minus mu 0. Now putting in the number from my null hypothesis over sigma hat times square root of n. Putting in these numbers is now our 98.5 minus 10, standard deviation 0.75 times square root of n is square root of 100. So you can take, of course, also a calculator. I will do it within Excel. So this is then hypothesis testing and mu and normal distribution, I call it. So I have x bar equals 9.85, mu 0, equals 10, sigma hat equals 0.75, and I think I had always the n in front of the other numbers, and this was 100, and then I obtain that equals, bracket opening, 9.85 minus 10 times square root of n over sigma hat equals minus 2. So, what do I have to do? Comparing this with our critical value. How do I obtain my critical value? So this has to be compared with the critical value CV. And there I told you the critical value depends, of course, on my error probability of my confidence level. And here I have alpha is 10%. So third critical value is obtained from alpha, and please do not forget this, the assumption on the distribution. So in our case, we have alpha is 10% and we have normal distribution, and thus, please, for the normal distribution, you should have in mind this picture, because then we know these values. And now you were absolutely right to specify the null hypothesis with mu is larger than mu0. And there you have to know that this picture corresponds to a two-sided confidence interval, two-sided test. So in these minus 2.58 means that this is 0.5% and this is 0.5%. So which number do I have to take when I want to take a one-sided test with 10% alpha? Which number do I have to take? Minus 2.58, minus 2.33, minus 1.96, or minus 1.64. So now the area under below only one tail have to be 10%. So alpha 10%, but one-sided, 10%. If I'm fast, then I say 1 minus 10% is 90%. Do I have to take then 90% here and the minus 1.64? Or well, let's take this in green. Of course, if I take this one here, then these two areas here below my tail both have to be 5%, because together they have to be adding up to 10%, and therefore I have to take the 95% interval here, because then I know, am I right? Sorry. 95, 2 point, no, sorry. I need even more, up 10% level, because then I have 2.5 only. Sorry. Oh. Then I need this number here. 1.23. So we have to take another one in here, because then I know that this area here is 10%. So this is more or less than the 80% area, and this is 10%. Sorry. Yes, thank you. You are absolutely right. So 1 minus 1.23, or roughly you can take minus 1.3. This is also okay. So then we move to our example. So then we know from a table or statistics software, we have CV roughly minus 1.32. And now again, I think you should have this picture in mind, that in this case, if our test statistics is within this area, then I can reject my null hypothesis. Then I think that my machine is out of order, that something is wrong. If my test statistics is in this part, then up to an error probability of 10% in my example, I just say nothing has changed. So then we have a minus 2 within this case, sorry. Then I'm not in today, I think. I have a minus 2. So I'm just really here, my critical value is minus 1.3. I have a minus 2, so up to an error probability of 10%, I can say that something is wrong with my machine. So since minus 2 is lower than minus 1.3, H0 is rejected. And I think you just should keep in mind these steps, and then you always obtain, or you use a good procedure and you obtain then the right result. Okay, then let's go to the next example. Within the distribution of some product, the sellers obtain a fixed income and a provision depending on their revenue. On average, a provision of 600 euro is paid. In the current month, the framework changed due to higher selling prices. Well, we know just here in our times, actually, all prices go up. And if I'm selling for higher prices just because the price level in the whole country has increased, then of course my revenue normally, my nominal revenue is higher. Or also, we just had Easter in the holiday season. I could say, well, in the holiday season, the people are somewhere in holidays, and therefore I cannot sell so many products. And therefore, there are maybe two reasons. The one reason would say that I would expect a higher revenue in this month of than the former 600, and the other reason, the holidays, from this reason, I can argue that I have lower revenue. I have a lower revenue, and then I just go into the data. What actually have done my sellers, and then I know really the average provision has been going down from 600 to 585. And now I want to know, do we have a significant lowering of my provision? Again, let's take H0. What would be H0? H0 would be my provision has not been lowered. Therefore, mu is larger than mu0. H1, mu is smaller than mu0. Second, test statistics, sample N100. And did I left out the number of... Oh no, here it is. Standard deviation is 80. X bar is 585. Let's take this here. X bar 585. Sigma hat equals 80. N equals 100. Then standard normal distribution. So we calculate our test statistic Z again is 585 minus 600 over 80 times square root of 100. This is roughly here. Let's just copy it. 800. This is now 600. 585. 80. So we obtain minus 8.75. Minus 1.875. Critical value 10%. So again, minus 1.23. And thus we have 4 minus 1.875 is smaller than minus 1.23. Do we have some time left? 11:30. Well, then let's do also this example here. Some new pharmaceutical product is for blood pressure should be up to 20 point. This we know from the advertisement. Is this true? Assume the parent distribution is normally distributed, but it is a parent distribution. Now we have a small random sample, small sample size. This means, together with the assumption that the parent distribution is normally distributed, just means we have to use the t distribution, and we have from our random sample n equals 9, x bar is 21, and sigma hat is 1.5. So now we know that our test statistic, oops, where is it? Here. This we calculate in the same way as in the other two examples, but this test statistics now we call t, since now we obtain the critical value not from the standard distribution, but we obtain it from the t distribution. And then we have to go into the table and looking up the number up corresponding to n minus 1 degrees of freedom. In our case, n minus 1 is 9 minus 1 equals 8. Oops. Here we are. So the same procedure as before. First, H0. Our pharmaceutical product should lower the blood pressure 20 points. In our random sample, we obtain, great, it is lowering the blood pressure to 21.5 points. So H0 would then be the assumption that nothing has changed in our case, so to speak. So mu is lower or equal 20 points. This we hopefully want to reject up to a level of 1%. H1 mu is larger than 20. Second test statistic. Now t x bar minus mu over sigma hat square root of n equals 21.5 minus 20 over sigma hat 1.5 square root of n, so square root of 9. Let's calculate this again. So we have 9, we have 20, we have 21.5, and we have 1.5, and we obtain a test statistics equal to 3. Third, we need the critical value. Now, from t distribution, Now I think we just go into the table, t-distribution. Or did you already have looked up the number? Then you can just give me the number. 4.51. This seems reasonably. So let's look at if I also can find this number. There we are. Oops. And t-distribution. This is the normal distribution. And here we are. T-distribution, we are n minus 1. So we have to go in n equals 8. So this would be here. Oops, where is my pen? There it is. N equals 8 and 1%. So I obtain 2.8965. Okay, well, this can happen, of course. 2.8965. 2.8965. CV is 2.9. Did we have 8965? 8965. And for we have 3 is larger than 2.8965. And hooray, up to our assumption. Again, this is the main point. T-distribution. Now, this T-distribution. Here is our critical value of 2.8965. Here is our test statistic equaling 3. And we are happy since we are within this area and therefore reject H0, and we are happy this product really is lowering the blood pressure more than 20 points, but of course using this given error probability. If you use another error probability, it could be the case that your critical value could be here. And there, this is also here the deciding assumption in your case. Of course, you can always find an alpha level where you are rejecting your null hypothesis. So using this alpha level has to be reasonably. And this is, this is what I sometimes think when people just in some talk show or if they are asked, is this or this true? Then they say, well, of course, I've made some experiment. I looked into the data and I can say that my result is statistically significant. And then that it is the statement. This is statistically significant. And there, the most important point is missing. Statistically significant for which level. This is the important information. Only saying this, my result is statistically significant, to be honest, this means actually nothing. Without specifying this number, of course, behind such a statement, we know that in general, a statement, my result is statistically significant, mostly means I used a level 1%, 5%, 10%, 0.1% or something like this. But I really need this information about alpha. Okay, so I think we are almost done, but we have only 2 minutes left. Then on Thursday, we also take another example where we just compare two samples and we want to know. So remember our first example introducing hypothesis testing. There I said 420 people out of 1,000. If we ask tomorrow another 1,000 people, the result could be 380 people out of 1,000. And now we can also compare these two random samples and want to decide up to a given alpha level, are they more or less, so to speak, is the result 380 out of 1,000, 420 out of 8,000, is this statistically more or less the same result? Because it is only a statistic fluctuation. And then the procedure is actually the same as before, only what we have to change is how do I calculate my test statistics, and I have to make an assumption about the distribution of these test statistics. And again, if my sample size is large enough, then I also assume that this new test statistic is normally distributed, and then I compare these test statistics with some critical value. Okay, so this we will do next week, and we close this lecture